Okay, section 5.4, polar coordinates, tangents to polar curves. So let's just go back from differetiation in normal maths. You met parametric differentiation. So dy dx could be expressed as dy d theta over dx d theta. It's just a chain rule. So you may recall it's more often than not it's written like this. So if you're looking for a tangent that is horizontal, so the traditional tangent, you are going to make dy dx equal to 0. Now that will happen when the top of the fraction, the numerator, dy d theta, is equal to 0. So this is what happens with polar coordinates. When you're looking for horizontal tangents, which are going across, then you're going to make dy d theta equal to 0, and it's called parallel to the initial line because that tangent is parallel to the initial line, which is over here. Now if you look back to this differentiation of parametric equations again, if you were to make the denominator equal to 0, you will get an undefined answer, so undefined gradient. So this means you are looking for the infinite gradient, so the tangent this way is going to be perpendicular to the initial line. It's going to be vertical. So we call it in polar coordinates perpendicular tangent to the initial line, and this happens when dx d theta is equal to 0. If you're worried that you are going to forget which one or get muddled up, which one represents which, I like to think of that as the horizontal tangent. So dy d theta, you are maximizing the y value. It's how the highest maximum value of y it will happen on that curve. When you are looking for perpendicular tangent, you are maximizing the x value, so you're going across as far as potentially you can on that curve. So this is what our class's definition of. Okay, let's move on to example 12, the first example, where this time we've got our curve that we've already had to draw twice, so I've drawn it for you. We're going to find the equation of the tangent that is parallel to the initial line, which I called theta equal to 0. Actually, we're not looking for the equation, we are looking for the coordinates of the point. So if it's parallel to the initial line, we are talking about this tangent, but also this tangent as well. So you're looking for those 2 points, okay? Because it's the equation involves cos, it's going to be symmetrical about the initial line. So once you've got one, the other one you just need to change the value of theta to opposite. Okay, so parallel to the initial line, we are going to maximizing the height, which is y. So dy d theta is going to be equal to 0. So I need to differentiate my y. But what is my y? Well, in polar coordinates, y is equal to r sine theta. So r is equal to a multiplied by 1 plus cos theta and then sine theta. So let's differentiate this expression, this equation. So we're going to say I'll use the chain rule, the product rule. 1 plus cos theta, v is equal to sine theta, u dash is equal to minus sine theta, and v dash is equal to cos theta. Then you've got dy d theta is going to be, there was an a here outside that I haven't taken into account, so I need to multiply them across. So it's going to be vu dash, so it's minus sine theta times sine theta, so sine squared theta, plus cos theta times 1 plus cos theta. So you're going to get minus sine squared theta plus cos theta plus cos squared theta. Okay, so now we need to solve an equation when dy d theta is equal to 0. So that will be equal to 0 when this here is equal to 0, the expression in the brackets. As I look at it, I could do with rewriting the whole expression in terms of cos only. So I'm going to change minus sine squared theta to minus 1 plus cos squared theta plus cos theta plus cos squared theta. So it's 2 cos squared theta plus cos theta minus 1 is equal to 0. Okay, so let's try and see if it factorizes. It may, yeah, because it should do. So you're going to get 2 is going to get a plus, this one is minus. Let's set up minus, there you go. Just check minus, yeah, that's correct. So there's 2 mini equations I must solve. Cos theta is equal to a half from the first bracket, or cos theta is equal to minus 1. So cos theta is equal to a half for theta equal to plus or minus pi over 3. So this must be that point. You could see that this angle here is pi over 3. Now cos theta is equal to 1 when theta, minus 1 when theta is equal to pi. So this actually corresponds to the this tangent here. So there's this point which I missed out to begin with, but clearly the algebra showed me that there's another point. Okay, so it's actually overlaps with the pole, but it corresponds to theta equal to pi. Obviously, for the full coordinates, we need to have the value of r. So this one is going to be a, and 1 plus cos pi over 3. So this is a half plus 1, so 3 over 2a. And for this one, it's got to be 0, but let's just check. R is equal to a, and 1 plus cos pi. Indeed, it's 0. So let me write down the solution. We are going to have 3 over 2a and plus and minus pi over 3. So that corresponds to these 2 points. And then the one here is going to be 0 and pi. Okay, moving on to example 13. This time we are asked to find the points of contact of the tangents to the curve. So the same process as before, but now for parallel tangents and perpendicular tangents to this curve. So I really quite like to draw this curve just to see what it looks like. So let me just get this. Okay, so this is just 2 loops, but we are only interested in the one between 0 and pi over 2. So sine 2 theta is going to be equal to 1. That will give me the maximum value. So 2 theta is equal to pi over 2, and then next time it will happen for because we have got to go up to 4 pi, so add 2 pi, 5 pi over 2. So theta is equal to pi over 4, and then 5 pi over 4. I know that we are only dealing in the first quadrant, but still nice to know. So it's for pi over 4. You're going to have the maximum value somewhere here, and then you'll have 1 over here. Right, then what are the limiting values? So sine 2 theta is equal to 0. Let's find out when it happens. For 2 theta equals to 0, pi 2 pi, 3 pi. Dividing it by 2 gives me 0, pi over 2, pi, and 3 pi over 2. There you go. So there's my loop. And there's the other one. Okay, but we're only interested in the one in there from 0 to pi over 2. So parallel to the initial line, we're talking about this point, and then perpendicular for part B, we're going to work out this point over here. So we need to differentiate our y's to find the one that's furthest up from the initial line. So dy dx, d theta, needs to be equal to 0. So let's find out what it is. It's 2a cos 2 theta. Let's make it equal to 0. So that happens when cos 2 theta is equal to 0. So 2 theta must be equal to pi over 2. But we're only solving between 0 and pi, so that's it. So theta is equal to pi over 4. Okay, in example 13, the equation is r equals to a sine 2 theta. You have a go into practice sketching the curves, so I'm just going to sketch this loop for you. But what I've done here is found out what the maximum value of r is, which happens to be a. That happens when sine 2 theta is equal to 1. So 2 theta is pi over 2 divided by 2 gives you pi over 4. Okay, what we need to do first of all, if we are looking for the points where the tangent is parallel to the, there you go, so it's this point parallel to the initial line, we've got to solve equation dy d theta is equal to 0. So let's find what y is. So remember, y is r sine theta. So in our question, it's r sine theta sine 2 theta. We've got to differentiate it. So dy d theta. Okay, so let's say u is equal to r sine theta. I kept a sine. And then v is equal to sine 2 theta. So u dash is equal to a cos theta, and then v dash is going to be 2 cos 2 theta. So differentiating these, we'll go times v by u dash, so you'll get a cos theta sine 2 theta, plus multiplying the other diagonals, you'll get 2 sine theta cos 2 theta. So now we need to make dy d theta equal to 0. So a cos theta sine 2 theta plus 2, forgetting a sine theta times cos 2 theta is equal to 0. This needs to be solved. Okay, so you've got your sine thetas and cos thetas, so 2 thetas and thetas modeled up. So what we're going to do, we're going to change our double angle to single angle and divide everything by a to get rid of this a. So cos theta stays as cos theta, sine theta is 2 sine theta cos theta, plus 2 sine theta, and then it doesn't matter which one you're going to use. You could use cos squared theta minus sine squared theta. You could have used 2 cos squared theta minus 1. Doesn't matter. Okay, so what we can do here, we can actually factorize 2 sine theta out, And then you've got cos theta times cos theta, which is cos squared theta plus cos squared minus sine squared theta is equal to naught. So we'll have 2 sine theta. I change that to coses, so it's going to be cos squared, and this one is going to be 2 cos squared. Let's just do it slowly. So 2 cos squared theta minus 1. So either 2 sine theta is equal to 0, so sine theta is equal to 0. That will happen for theta is equal to 0. This corresponds to this tangent over here. Since we've been told to start from 0, this is one of the tangents, okay, so it's perfectly okay. Now the other one, this will go to 3 cos squared theta equals to 1. So cos squared theta equals to 1/3. So cos theta could be plus or minus 1 over root 3. Because we're only going up to pi over 2, we only need to solve cos theta equals to 1 over root 3. So you can use the calculator to find out because it says if appropriate, round your answer to 3 significant figures. So do cos inverse of 1 over root 3. That gives me theta equals to 0.955 radians. But this is only this is only part of it. We need to find the corresponding values of r. So for the first theta equals 0, r is going to be equal to 0 as well, if I sub it into the equation. Now over here, to find the exact value of r, which is possible, even though theta is not a nice angle, we are going to use the formula a sine 2 theta and replace it, sine 2 theta, with the double angle formula. There you go. So what we need to do is find, we've got cos theta is 1 over root 3. Now we need to find sine theta. So let's just use a right angle triangle method. If that's theta, if cos is 1 over root 3, we're going to do adjacent as 1 and hypotenuse as root 3. So opposite must be root 3 squared minus 1 squared square rooted, so it's 3 minus 1, so it's root 2. So for this one, for an acute angle, because we are working between 0 and pi over 2, sine is positive, root 2 over root 3. Let's pop these into our expression here, equation for r. Sine theta is root 2 over root 3. And cos theta is 1 over root 3. So you've got 2 root 2 over root 3 times root 3, so over 3. So 2 root 2 over 3a. Let's pop the 2 points. So the first point is going to be 0, 0. And the second point is 2 root 2, 3a. And I'm afraid we have to use the rounded answer for the value of theta. Let's go on to part B. So part B of example 13. So this time we're going to be looking for the perpendicular tangent, so there will be 2. Okay, now this one here is going to be maximizing the values of x, if you like, on that curve. What's the biggest value of x you can have on that curve? So let's do part B. So it's dx d theta needs to be equal to 0. So if x is r cos theta, then in our equation we need to times a times sine 2 theta by cos theta. I'm just doing the same thing but with x's. So differentiating this, we're going to have u is equal to a sine 2 theta and v is equal to cos theta. So u dash is going to be 2a cos 2 theta and v dash is minus sine theta. So it's going to be vu dash plus uv dash. So it's 2a cos theta multiplied by cos 2 theta minus sine theta a sine theta multiplied by sine 2 theta. So we're going to solve in a very similar way as before. So we're going to make it equal to 0. Need to replace the cos 2 theta and sine 2 theta using the Revoir formula. So it's going to be 2a cos theta. Again, you've got 3 versions of that. I'll use this one. 1 minus 2 sine squared theta. And then you've got minus a sine theta multiplied by 2 sine theta cos theta. Okay, I'm going to factorize cos and factorize 2. I'll just divide by a. In fact, I'll divide by 2 as well. So let's factorize cos theta. Remember, never divide by something that can be solved, where it can be equal to 0, just factorize it. So it's 1 minus 2 sine squared theta, and over here it's minus cos. No, factorize cos is minus sine squared theta. There you go, that's good. So you've got cos theta can be equal to 0, or now if you tidy this up, you've got 1 minus 3 sine squared theta is equal to 0. That gives me sine squared theta is equal to 1 over 3. So sine theta is equal to plus or minus 1 over root 3. Again, we're only going to pick positive because we are working in the values between the 0 and pi over 2. So we've got to reach for the calculator again and do sine inverse of 1 divided by root 3. That gives me theta equal to 0.615 radians. So we've got to give this, but we need to find the value of r that corresponds to this angle. So what is the value of r? Well, r is equal to a sine 2 theta. So this is going to be 2a sine theta cos theta. So sine theta is 1 over root 3. Now cos theta, I'll just go through the same process as before, but you'll probably guess what it will be. Okay, so this time it's sine, so opposite over hypotenuse is 1 over root 3. Then this side needs to be root 2. So cos theta would be root 2 over root 3. There you go. So it's going to be 2 root 2 over 3a. Now, this solution to that question here, we have almost missed it out. Theta is going to be equal to pi over 2. And the value of r, if I put pi over 2 into this one, it's going to be a sine 2 times pi over 2, which is 0. Okay, so that corresponded to the this point here. So this point here is going to be 0 pi over 2, and this point here is 2√2/3a, and then 0.615. There you go. They've also, I've just noticed, they've also asked us to find the equation of the tangent. So I'll go back to example A, and we'll find the corresponding equation of that tangent at that point, and then we'll do the same for part B. So what we've done in part A, we found that that we wanted to know this equation of that line. The equation of this line here is really simply initial line. So this is the equation for that lower tangent. Now to find the higher tangent, okay, so let's think what it is. So let's just label it. So equation of tangent parallel to the initial line through the point, and the coordinates of that point are 2√2,3a and 0.955. Okay, so this is what you need to do. If you were working on the Cartesian plane, so Cartesian equation, is simply going to be y equals to the y coordinate. So we need to find that y coordinate of our point that we've got given in polar coordinate. So what's the y coordinate? So this is going back to the initial part of the chapter where you learned to change polar coordinates to Cartesian coordinates. So the polar coordinates are 2√2/3a, and then theta is 0.955. So what is the definition of a y coordinate? Well, it's r sine theta. So the value of r at that particular point is 2√2/3a, and sine theta, okay, we're not going to put sine of 0.955 because we actually know that sine is √2/√3. So it's √2/√3. So the actual y coordinate is 2 times 2, so it's 4a and 3/√3. Over 3√3. You can change it, rationalize the denominator. So this is our equation. Y using this information is equal to 4a 3√3. Okay, now this is Cartesian equation. Let's now, still going back to what we've learned at the initial stages of the chapter, the polar equation. So we're looking for all the points that satisfy this equation. So we just need to replace y with a general form of y coordinate. So it's r sine theta is equal to 4a over 3√3. So r is equal to 4a 3√3 divided by sine theta. That will go to cosec theta. Okay, so let's go on to the same question but part B. So it's very similar. Okay, so here is our just get a piece of paper. Just use this one. Okay, so what do we know? So we know that we found two tangents, okay? One that goes through the point 0 pi over 2, and the other that goes through the point 2 root 2 over 3a and 0.615 radians. So the one that goes through 0 through and pi over 2, so it's this one here. Let me just write down clearly, 0 pi over 2. So this one here is simply going to be your theta equal pi over 2. It's just what positive y-axis over here. So the second one is, this time we're looking for vertical tangent, which is perpendicular to the initial line, and it goes through the point 2 root 2 3a and then 0.615. Okay. So let's just do the same, go through the same procedure as before. First of all, if it's a vertical tangent, then it's going to be x equals to the x coordinate. So at that particular point, the x coordinate, which is r cos theta, is going to be, r is 2 root 2 over 3a, and cos theta we found earlier on to be root 2 over root 3. So it's 4a 3 over root 3. So now that would be a Cartesian equation. So x equals to 4a 3 root 3. This is a Cartesian equation. The polar equation, you just need to replace all the x's with their general polar form. So r cos theta must be equal to 4a 3 root 3. Rearrange it, divided by cos. If you divide by cos, bring it to the top rather than writing 1 over cos theta. That will change to sec theta. And this is our tangent that is perpendicular to the initial line. So look at example 14. So here we're going to have a proof of the condition for a dimple and no dimple. So remember, dimple exists if p is less than 2q, and there will be no dimple if p is greater than 2q. The way I remember is p over q is greater or equal to 2, p over q is less than 2. Okay, so we're going to use the idea of looking for the tangent. So let me just draw the curve that possibly has a dimple. So it may look like this. Now if it has a dimple, it will have a tangent here, a tangent here, and a tangent over here. So let's just see what happens. So looking for perpendicular tangents, and let's see how many of them we're going to have. If you have a no dimple, then we're talking about one here and one here. Okay, so let's find what x is, because for perpendicular tangents dx d theta is going to be equal to 0. So x in our instance is r cos theta, but r is equal to p plus q cos theta multiplied by cos theta. So let's differentiate it. So dx d theta, I'll do it a little bit quicker. This is my u, so we're going to differentiate it and multiply it by cos theta, and then do it the other way around. So it's going to be minus q sine theta cos theta, and then you're going to differentiate cos theta, which is minus sine theta, and multiplied by p plus q cos theta. So let's factorize minus sine theta out, and you are left with q cos theta plus p plus q cos theta. We're going to make it equal to 0 because dx d theta is equal to 0. So it will happen for sine theta equal to 0, and sine theta is equal to 0 for 0, and then pi. And then the second one is 2 cos theta, 2q cos theta is equal to minus p. So cos theta is equal to minus p over 2q. So here we need to consider, if our p is going to be less than 2q, let's see what happens. So if p is less than 2q, if it's less than 2q, so the numerator is smaller than the denominator, then you will have a solution. Cos theta is equal to minus p over 2q. We'll have two solutions. Now, because it's minus p over 2q, that means that the two solutions, cos theta is going to be negative in the third and fourth, in the second, and third quadrant. So any value between 90 up to 270, which is pi, and 3 pi over 2 gives me negative values. So two solutions. So if you think about considering this case, so you will have a tangent at 0, which is this one, and then you're going to have a tangent at pi, which could be this one here, and then you will have two solutions. So tangent at the second quadrant, see this angle over here, that's going to be more than 2 pi over 2, and the third quadrant. So this here is a dimple. The only way you could sketch this curve with that many tangents if the curve has a dimple. So let's now consider p equals to 2q. And that way cos theta is going to be equal, so if you put 2q over here, that will give me minus 1. And theta, the solution to that equation, is going to be pi. So you have a tangent for theta equal to pi, and then tangent for theta equals 0 as well here. So it's this situation, so no dimple. It's a convex curve. Now if p is greater than 2q, then cos theta, you will have the value is going to be let's say modulus of that greater than 1. Okay, so it's actually no solution, because you will have something that's between 2q, bigger than 2q over 2q, the value is going to be minus 1 point something. It's a bigger value than in size than 1. So no solutions. So if no solution, no dimple, because you are only going to have two solutions from sine theta equal to 0, which corresponds to this one. That could be for theta equal to 0 and theta equals to pi. So here's your proof. Okay, so you are ready to go on to 5D, and this completes the chapter. You've got mixed exercise.